Alright guys, so we're going to go over another electrolytic cell problem. So for this one, it gives us an image already, so which is very helpful. And it tells us that magnesium is produced commercially by electrolysis. Now if you guys remember, the term electrolysis always tells you that it is an electrolytic cell. So that means that the reduction potential has to be negative because it is non-spontaneous. Okay? And we can see that because there's a voltage source or a battery involved here. And it's commercially produced by electrolysis from a molten salt using a cell similar to the one shown below. So we got this right here. Now, a couple things that we should notice right away is that there are two electrodes. So we got a steel electrode and carbon electrode. And if you remember, these metal bars in electrolysis do not, or they're not part of the reaction. So it's not like you're going to add steel or carbon to your chemical reactions. You should also notice that we have magnesium and we have chlorine gas. Okay, that means that there's magnesium and chlorine involved in this reaction. Now, if you look right here, it tells you that it's formed from a molten salt, and it tells you that you have electrolytes here. Electrolytes are ions, so you should automatically identify that there is going to be Mg2+ involved in here somewhere, and Cl-, because those are the electrolytes or ions associated with magnesium and chlorine. All right, that's actually going to help us answer part A, because part A is asking, what is the salt used as the electrolyte? Well, if the two compounds that are involved in this reaction are magnesium and chlorine, Mg is 2+ from its most common ion, chlorine is -1. That means that the salt that we're going to produce, the ionic compound that we make, is going to be MgCl2. Okay, so that's the answer to part A. Pretty easy. And we can identify that because there's magnesium and there's chlorine. Next, it's asking which electrode is the anode and which is the cathode. For this one, we're going to use our acronym, REDCat and ANOX. So reduction happens at the cathode, and at the anode, there is oxidation. So if these are our electrolytes, we're trying to figure out how do they get from the electrolyte form to what's given in the picture. Now, if you look, it looks like Mg2+ is becoming liquid magnesium. So Mg2+ is becoming liquid magnesium. Now, liquid magnesium does not have a charge. That means it is neutral, so it is 0. So we're going from 2 to 0. Okay, now if you look, we have +2 and 0. So if we go from +2 to 0, we are going in the negative direction. That means we are gaining electrons. So Mg2+ is gaining 2 electrons to become liquid magnesium. If you gain electrons, if you remember, that is reduction. And reduction happens at the cathode. That means that the steel electrode right here is going to be our cathode. So for our answer for part B, the cathode is going to be the steel electrode. Which means right away we can automatically know that the anode is going to be our carbon electrode. However, we can also test this independently without knowing the other one. If you take a look right here, what's happening at the carbon electrode? It looks like Cl- is turning into chlorine gas. Okay, as you can see right here, there's a bubbling and the chlorine gas escapes. Well, in order for Cl- to become chlorine gas, which is neutral, so a charge of 0, that means that it needs to lose electrons. And in order to balance this, we just put 2 chlorines, make Cl2, and there are 2 electrons. So it is losing electrons, which means it is being oxidized, and anox, oxidation happens at the anode, so the anode is going to be the carbon. All right, doing it this way is actually very helpful because we have a question that's asking us to find the individual half reactions. Well, we wrote them already. This is going to be our reduction half reaction, and this is going to be our oxidation half reaction. And then we got to write the overall cell reaction. Pretty simple, Hess's law. The electrons cancel out with each other, and we just combine them together. So we got Mg2+ plus 2 Cl- produces Mg liquid plus Cl2 gas. And this is going to be our overall reaction. Okay, now, there is something that I do want to mention. If you have it like this, that should be fine. However, this question does specifically say that we have a molten salt. So this area right here where it says electrolyte, this teal color thing, this is the molten salt. And the molten salt is MgCl2. So we can combine this to MgCl2 liquid and then complete the reaction as well. Okay, not totally necessary because the image tells you electrolyte, and electrolyte means it's ionized, so this is fine. But the question says molten salt, so we can also infer that it is a liquid salt. So that is an example of another electrolytic cell problem. All right, so we're going to try another electrolytic cell problem. This one is actually going to be from the 2005 AP exam, so it's a very long time ago. This is even before I took the AP test. And it tells you that an electric current is applied to a 1 molarity NaI solution. And if we take a look at it, it's very similar to the example that we learned electrolysis from, where we had the 4 reactions, and we're trying to figure out what the overall reaction is. So what we're going to do here is we're going to take a look at this reaction right here, and we want to figure out, because it is electrolysis, it is non-spontaneous, right? It is not thermodynamically favored, which means that the reduction potential has to be a negative number. However, not only does it need to be negative, it needs to be as close to 0 as possible. All right, so we need to figure out which one first is going to be our reduction, and then we need to figure out which one we're going to flip. Okay, now we're going to pick the reduction one first because we have our values. This is positive, so we can't pick these for reduction. These are going to be our options for oxidation. Okay, the ones that we're going to flip. And these two are going to be our options for reduction, because they are both negative. Well, they're both negative, but we want to get as close as possible to 0. And so if we take a look at this reaction right here, the third one, this one is a lot closer to 0 than this one right here. And so we are not going to pick this fourth one because this one is a lot further from 0 than this one. So this right here is going to be our reduction half reaction. So we can copy it down for part B. Our reduction half reaction is the one that is closest to 0 and is negative. All right, moving on. We're going to take a look at part A. A is asking for the oxidation, so we're trying to figure out which one we could flip, and when you combine it with this one right here, we can get as close to 0 as possible. Well, if we flip this first one, it'll become negative 1.23. The second one will become negative 0.53. And obviously, you should be able to see that adding the second one with this one is going to give us a negative number that is as close to 0 as possible. So that means that our second one is our option for oxidation. But remember, when we are doing the oxidation, we need to flip it. So it's going to be 2I minus plus, oh, excuse me, not plus, and then our arrow, I2 solid plus 2E minus. And since we flipped it, the reduction potential will be negative 0.53 volts. And this one will be negative 0.83 volts. All right, next step, we want to figure out what takes place at the anode, the oxidation or reduction. Well, this is very easy. We just need to remember our acronym, REDCAT, ANOX, and then we can just see that at the anode, there is oxidation. So the oxidation is going to happen at the anode. And then if you really wanted to, you could copy down your oxidation one, which is your answer for part A. So 2I minus produces I2 solid plus 2 electrons. All right, last question is kind of combining what we learned in the previous unit with thermodynamics. All electrolysis reactions have the same sign for delta G. This is a statement that we're making. And it's basically just asking, is delta G going to be positive or negative? And you want to justify your answer. Okay? If you remember from Unit 13, a positive delta G means that it is going to be non-spontaneous. Okay, whereas a negative means that it is spontaneous. It's the opposite of reduction potential. Okay, so we know that electrolysis is always non-spontaneous, so our answer is going to be that delta G is always positive. And then you would say something along the lines of delta G is positive because electrolysis is always non-spontaneous or thermodynamically unfavorable. Okay, so that's the answer to part D. All right, everyone. Now we are going into the last topic of AP Chem. Congratulations on making it all the way here. The last topic is something called electroplating. Okay, electroplating happens in electrolytic cells that are used for electroplating, and basically it's where we have this right here, where you have your electrolyte in an electrolytic cell, and then a metal plates out or kind of solidifies. And this formula is actually on your AP equation sheet, but basically what this allows you to do, it allows you to figure out how long it takes for a certain amount of metal to plate out or solidify in an electrolytic cell. So if we pull up our AP equation sheet, at the very bottom, you will see this equation right here. Now, before we move on, I want to highlight what the units of measurement are going to be. I is the current, and it is in amperes. Q is the charge in coulombs, and T is the time in seconds. Keep that in mind. If you are given time in a different unit of measurement, then that means you have to convert it to seconds if you're going to use this formula. This is used often in conjunction with this right here, Faraday's constant F, and F is not the one that we're really going to use. This equation is not used very much, but what we need to know is that F is equal to about 96,000 coulombs per mole of electrons, and I'll show you how to use that in a second. All right, so the easiest way I think to do this is to solve a problem, but basically what electroplating allows you to do is figure out how much metal you can plate out in an electrolytic cell or how long it takes to plate out a certain amount of metal. So we're going to do a problem, and I think it's the best way to learn this. All right, so if we take a look at 11, 11, it gives us some values. It says if a current of 2.5 amperes, now we just saw on our AP equation sheet that amperes is a measurement for current, for I. So this right here is going to go in our equation as I. And then it gives you the solution, iron 3 chloride. Iron 3 means that it is Fe3+. Chlorine is -1, so if it's iron 3 chloride, that means that our compound is FeCl3. And the time is given in 15 minutes. Okay, but we need to convert this to seconds. And then it's asking, what is the mass of iron to plate out? Now, mass is always measured in grams, so we are looking at grams of iron. All right, now, if we take a look, we are given two numbers in this problem, and the two numbers are I for current and T for time. So our time, we can very easily convert it to seconds by multiplying it by 60, and that'll give us 900 seconds. So we have I and T, so we're going to plug it into the equation from the AP equation sheet. I is equal to Q over T. If we rearrange it, the only thing that we don't, or if we plug in our numbers, it'll be 2.5 amperes equals Q over 900 seconds. So we can solve for Q here. Q is going to equal to 2.5 times 900, and that'll give us 2250. Now, we're probably not very familiar, unless you took physics, finding out the units of measurement for charge, but it gives us to us in the AP equation sheet. If you use ampere for I and seconds for time, we get charge in terms of coulombs. So it's going to be C, so 2250 C. Now, we are not trying to find coulombs, we are trying to find grams of iron. So what we're going to do is we're going to take our number, 2250 coulombs, and we're going to convert it slowly to grams of iron. Now, we need to get rid of coulombs, but what can we turn coulombs into? And this is where we're going to look at the AP equation sheet. I mentioned earlier about Faraday's constant. Faraday's constant is the only thing that we have anything to do with coulombs. So what we're going to do is we're going to plug in 96,485 coulombs on the bottom of our fraction. That's going to allow us to cancel out coulombs. And then it is equal to 1 mole of electrons, so we're going to put 1 mole of electrons. going to use this right here, Faraday's constant. Now, we don't want moles of electrons. We're still trying to turn it into mass of iron. So we need to get rid of moles of electrons and turn it into iron. Now, this is where we look at our formula, iron 3. Okay, iron 3 has a charge of 3 plus. How many electrons does it take to balance that out? Well, since it's iron 3, it takes 3 moles of electrons for every 1 mole of Fe3 plus. And that's going to allow us to cancel out moles of electrons. Almost there. We're turning moles of iron into grams of iron. That's pretty easy. That's just molar mass. And we know that Fe3 plus weighs the same as Fe because electrons don't affect the mass because it is negligible. So if we take a look at our periodic table, we can see the molar mass of iron right here is 55.84. So we're going to plug in 55.84 grams per every 1 mole, and the moles cancel out. And there you go. That's how you can turn current and time into grams of iron. Okay, you plug that in your calculator, and you should get 0.43 grams of iron. So in this electrolytic cell with this current, and if you run it for 900 seconds, you will plate out 0.43 grams of iron. So if you look at this is actually a lot of just stoichiometry. So if your stoichiometry and dimensional analysis is solid, this should be a pretty easy type of problem. All right, take a minute, pause the video, and I want you guys to try 12 on your own. All right, welcome back. We're going to try 12, and for 12, we're going in reverse. This time, we are given our mass, which is 2.22 grams of Ag, and it tells you the formula, which you should identify as AgNO3. Ag, silver 1 is Ag plus. Nitrate, one of the polyatomics you need to memorize, it's -1. So it becomes AgNO3. All right, so it gives us another number, which is 2 amperes, okay? So we know that if you take a look, the question is asking how long, and that means time, right? So we're looking for seconds. So if we look at the equation sheet, we should get this for our equation. We are looking for time. We have amperes. It's 2 amperes for I. That means if we find Q or coulombs, we can figure out this problem. So we're going to use the other values that we have to figure out coulombs. So this problem is just reverse of the previous one. So 2.22 grams of Ag, we want to turn into coulombs. And if we looked earlier at the equation sheet, we can find coulombs using moles of electrons. And we can find moles of electrons by finding out how many moles of Ag we have. Because we know that Ag here is Ag plus. That's going to be equal to 1 mole of electrons for every 1 mole of Ag. All right, so first we got to find molar mass to convert into moles. Ag, if you look at the periodic table, is 107.87. So 107.87. That's grams of Ag, and that is per mole of Ag. Okay, next, we know that 1 mole of Ag plus is 1 mole of electrons. So 1 mole of Ag plus is 1 mole of electrons. And we know from Faraday's constant that 1 mole of electrons is 96,000, what is that value? 485 coulombs. Okay. And then we plug that into our calculator. You should get about 86 coulombs. And then we plug that into our equation right here. We are solving for time. Time is going to equal, if we rearrange it, Q over I, and we plug in our values. 1986 coulombs divided by 2 amperes, and that's going to give us 993 seconds. All right, everyone, we are about to get into the last question of AP Chemistry in terms of the lecturing. All right, and this has to do with it's not actual numbers for electroplating, but it has to do with the concept. So Here it tells you that a strip of metal X is placed in a solution containing Y2 plus ions and there is no reaction. So in this scenario, what we have is a container and a piece of metal, we'll call it metal X, is placed in a solution of Y2 plus ions and there is no reaction. Okay, however, there's another situation where metal X is placed in another solution containing Z2 plus, and metal Z forms on the strip. So what's happening is here we have Z2 plus turning into solid zinc on the surface. So there's no reaction for this one, but there is a reaction where Z2 plus aqueous turns into solid zinc. And the question is asking to organize the reduction potentials of X, Y, and Z from greatest to least. All right, so for this one, it's pretty simple. We basically just need to figure out what the reduction potentials are relative to one another. So we're going to start with this one right here, X and Y. There is no reaction here. Okay, basically what that means is Y2 plus cannot take electrons from X. Because in order for Y2 plus to plate out or solidify on the surface, that means Y2 plus needs 2 electrons to turn into solid Y. Okay, but it cannot do that, which means Y has a lower reduction potential than X. So Y's reduction potential is less than X. On the other hand, here, not Zn, excuse me, Z2 plus can turn into Z solid, which means that Z is able to take electrons from X. So it is able to take electrons. So this works out. Since it is able to take electrons from X, we can assume that Z has a greater reduction potential than X. So putting that together, that means that Z has a greater reduction potential than X, which has a greater potential than Y. And then we look at it, and then that is going to be answer C.